Thank you everyone for coming for the talk, and I promise to keep it short so that we can all rush for lunch. A bit of introduction about myself. I'm a graduate student at University of Montreal right now in my second year of masters. I've been using Numpy, PyTorch, Python for a long time, Python for almost for 7 years, Numpy for last 6 months, though I have made some upstream changes to PyTorch as well. And what I'll be talking about is a bit about NumPy, a bit about PyTorch, and then why should anyone use PyTorch at all? What are the pitfalls of using PyTorch, and basically what is missing in PyTorch, and what's like the way ahead? How many people here have used list, like the list, Python list? And how many have used NumPy arrays? And what's the fundamental reason for using a NumPy array? It's faster. It gives you a lot of inbuilt techniques. It gives you a lot of inbuilt tools already. I'm not sure why this red line is coming. I thought I was in incognito mode. Oh, I wasn't. My bad. Let's do it again. Right. So when we use NumPy array, the primary reason which is given is that it's much better than this list because it has got this homogeneous data type and iteration, and everything becomes much faster and so on. The entire NumPy story is built around this ND array, an n-dimensional array, which is the first class primary data citizen in the NumPy stack. And you have a lot of fast routines and fast functions built on top of this ND array. So you have this ND array, which is the first class citizen, and everything is built around this ND array. Other flexibilities which NumPy gives you is integrating with C, C++, or Fortran code, which I'm sure most of us don't write anymore. And then, as I said, benefits over the inbuilt Python sequences. Oops. Given a list, it's pretty simple to transform it into a NumPy array. All we have to do is call an np.array. And that's part of the appeal because it makes it very easy to migrate from a list to a NumPy array. And a couple of examples showing things that you can do in list can be easily done using NumPy arrays. And then example showing that you have all the inbuilt techniques and functions which helps you to get rid of a lot of for loops. And this is a canonical example where you have a list of a lot of elements, and then you have an array of a lot of elements. You execute the same operation over them, and then you say, voila, NumPy is much, much, much faster. The reason I'm going over these things is because I'm going to use the same arguments when I would pitch you to use PyTorch as a replacement for NumPy. So the kind of things that we saw, it's very easy to migrate from a list to NumPy. It gives you the same amount of flexibility. You can do the same things that you were doing in a list. Now you can do the same things using NumPy array, and that it's much faster. I'm going to make all these arguments once again once we start talking in terms of why should one migrate from NumPy to PyTorch. So PyTorch. PyTorch is basically a machine learning framework, but we would not be focusing on the machine learning aspect of it. We would be focusing on more of the NumPy-like aspect of it. Its development was initiated at Facebook AI Research, which is like a small core team within Facebook. And where PyTorch is very similar with NumPy is that just like NumPy has this core ND array, PyTorch also has something which is very analogous or very similar to this ND array. And on top of it, PyTorch provides you GPU acceleration. So it has got this ND array kind of a construct, and on top of it, it's allowing you to use better hardware. The other part of PyTorch, which again we would not be diving into, is that it can be used to make deep neural networks using automatic differentiation. Again, we would not be going into this part. Part of appeal for PyTorch is it's Python first as compared to some other deep learning frameworks which are out. It provides you a hybrid front end, which means you can write Python as well as C, and the same code would execute. It supports distributed training, and it has an ecosystem of solutions and so on. Just to give a top level picture. Now, the first point, the key selling point about PyTorch, which I want to convey here, is that it supports tensor computations just like NumPy does. A tensor is basically an n-dimensional array, so NumPy calls it as ND array. Torch calls it as tensor. And now, given that NumPy had this first-class citizen, PyTorch has this another first-class citizen, we are going to see how is there a one-to-one mapping between these two constructs. So first of all, how do we make our NumPy array? We would probably do something like np.once, and I would just pass in a shape, and I would get this NumPy array of shape 2, 3, which has all the values filled as 1. If I wanted to do the same thing using Torch, all I would do is all I would do is this np.ones would be replaced by torch.ones. That's it. That's the only difference that I do. So the creation operations are very, very similar. This np.ones has been replaced by this torch.one. Of course, there was an import statement where I wrote import torch, but once you have done that part, the APIs are very similar. If you are doing something like np.i and then you are adding two numpy arrays, again, the exact same thing can be done in torch. np.ones would be replaced by torch.ones, and np.i would be replaced by torch.i. In fact, when I was writing these examples, I just wrote the numpy examples, copied that code, replaced np by torch, and everything worked out. So the first part of appeal is that if you are already familiar with numpy, it's very, very easy to start working with torch tensors because the API is very, very similar. So this is like the first part of appeal as to why should you even think about doing this transition, because this transition is very seamless. It's not really, you are not learning a new framework. If you know numpy already, you know torch already. And then there are a couple of other examples where, like the way you make an np.array and then you pass in a list, the same way you can write torch.tensor and you can pass in another list. And this list would become a tensor. A tensor is fundamentally the same thing as an ND array. It's just the name is different. Now, sometimes, so there are two ways of doing this assignment variable assignment thing in NumPy. Either you would write an equal to expression, or you would have something like np.sum, and then you will pass an optional out parameter. The point of passing the optional out parameter is so that the intermediate variable does not need to be created, and you can directly write into the memory where you want to write. So you basically eliminate one extra variable. The same thing is supported in Torch with the exact same API. So just like you had this x and y, there are two ways of adding it. One way is where you say y is equal to np.add x comma y, and you do an explicit assignment. The second way could be where you invoke the np.add function, pass in the two ND arrays, because this is NumPy, and then you say that the output should be written into the memory which is taken by y. Again, the exact, So this is the assignment thing, and this is the second way where you directly write it into the memory. The same thing is supported again. All that I did was replace np by torch, so I could have the assignment case as well as the case where I'm directly writing the output to the memory. Again, it's if you have already been using NumPy, it's very easy to migrate into the torch kind of setup. So I should say most of the tensor operations have an API which is very similar. Even things like advanced indexing, where you have this weird sort of indexes with strides and everything, and you are indexing into a NumPy array, the same thing can be done with PyTorch. So this is an example of advanced indexing in NumPy, which is a very standard thing for NumPy. You have got this array of 10 numbers, and then you're striding into the first and like different elements with a different stride and so on. Again, in this case, you can just replace np dot everything. Like you can just replace np by torch, and everything works as it is. So all those fancy indexing things which NumPy supports you, which is kind of a part of its appeal, are already supported in Torch. Even negative strides and negative indexes and so on, these things are also supported in Torch. Again, so far all I'm conveying you is it's very easy to use Torch if you already use NumPy. You are not really learning a whole new API. But there are some differences. It's not a one-to-one mapping. The key difference probably is that for a lot of operations, NumPy uses this keyword called as access, which you pass in a lot of function calls. This access gets replaced by dim. So this is one kind of big difference. Instead of a copy function, you have something called as clone in PyTorch. And instead of np.expand dims, you would call something like unsqueeze. Instead of tile, you would call something like repeat. So there are some differences, and it's not a one-to-one mapping, and these differences have been kind of more completely described here. The other difference is, for example, I have this np.linear space, which is taking parameters start, stop, and num, whereas in Torch, it would take the parameters start, end, and steps. So even though the output is exactly the same, I mean, like, other than the fact that this is using a 1-point precision while this is using a 4-point precision, the output is exactly the same, even though the name of the variables might be slightly different. Like, for example, instead of stop, I'm using end, and instead of num, I'm using steps now. So the APIs are similar, but PyTorch is not a drop-in replacement. So you cannot just take PyTorch and start using it everywhere. But this is not as bad as it sounds right now. Like, we'll see later yes, this difference exists, but it's not like really a breaking point for us. Before I go into the part of what extra functionality is provided by PyTorch on top of NumPy, I would pause for a minute and I would ask the audience if they have any operations in mind which they frequently do in NumPy, and they want to make sure whether this exists in Torch or not. Anything like, I do broadcast multiplication, something which you think is useful for your use case, and you just want to make sure whether this exists in Torch or not. Yes, it is there. In fact, I think it has been added in the latest version, but it is there. For people who use discrete Fourier analysis and other crazy things, okay, I don't use any of the DFT stuff, but for people who use that kind of stuff, again, that support is also there in PyTorch. So the entire point of this part is to make sure that if you have a use case which you think is super useful in NumPy, and you just want to make sure whether that thing is supported in Torch or not, then you should just ask about it. Okay, so first thing is, it seems most of the use cases that people have are covered in Torch. So next, the question comes in, well, NumPy is working good for me. Why should I migrate to a new code base, to a new ecosystem, essentially? Primarily because it gives you GPU acceleration. So recall when we were talking about migration from list to NumPy arrays, we said that speed becomes a critical factor. I can get much faster results when I'm using NumPy arrays instead of list. There's a small catch there. When you migrate from list to NumPy array, you are improving your software. Your hardware, your computer, your device where you are performing these computations remain exactly the same. But when you migrate from NumPy to PyTorch, the acceleration or the speed up that you get is not because of the software, it's because of the hardware. So if you have better hardware, if you have a GPU device, then you can harness its power with Torch, but not with NumPy. So it still gets you better, it still gets you faster results, but it's not faster because of the software, it's faster because the software is allowing you to interface with the hardware. To go into that canonical example, now I'm making an NP array, and I'm computing a matrix, I'm doing a matrix product, and that takes around 36.6 seconds. When I do the same thing in Torch on a GPU, again, I'm hyper-emphasizing that the acceleration is coming from the hardware, not from the software. Then I get my compute time from around 35 seconds comes down to under a second. So yes, it gets you acceleration. That acceleration is not coming from the software, but it is the software that is allowing you to do this interfacing with this sophisticated hardware. And GPUs are not really like this unique kind of thing now. Companies are coming up with enhancements over GPUs, things like TPUs and so on, which would be even more well-suited for doing all these kind of tensor manipulations or matrix manipulations instead of things like NumPy. So nothing wrong with NumPy. The only thing is it doesn't let me access a better hardware when I have it. So if I don't have a better hardware, probably I'm all good to go. But if I do, then I cannot do this thing using NumPy. Now, this is all good, but I do not want to rewrite my code into Torch. I have my NumPy code. In fact, most of the time when you write this code, there would be some operations, some specific operations which would be the bottleneck. There would be some operations where you would be doing a big, huge matrix multiplication, and everything else would probably be good to go in NumPy itself. So I do not want to rewrite my entire code just to fix those 2, 3, 4 lines of code. So is there a workaround for that? Can I just use Torch whenever I want, and for every time else I can remain in NumPy? Turns out, yes. We have this bridge between NumPy and PyTorch. So you can take a NumPy array, and you can convert it into PyTorch array. And similarly, you can take a Torch tensor and convert it into an ND array. The good part is you're not really creating a copy of your data. The underlying memory is shared between PyTorch and the NumPy ND array. So you'll have some data blob in the memory. NumPy would have defined an ND array view on top of it. Torch would have defined a tensor view on top of it, and both of them would be able to use it. So even if you were to map your NumPy array into a PyTorch tensor, you are not really creating a new copy of the data. So it's not that you had a huge matrix, and now you want to go into tensor, and now you are creating a copy of that tensor. It's not there. The memory is being shared. So really, the cost is not that high. So at least in terms of efficiency, the cost is not high. Now let's talk about the developer efficiency. That's all you need to do. You have a NumPy array. You call torch.fromNumPy, and you have a torch tensor. That's it. And if you want to go back from PyTorch to NumPy, all you do is .NumPy. So since the memory is shared, there is no cost in terms of creating a copy of the data. And from a developer's perspective, again, it's a very, very, very small piece of code. This is just one small code which shows that I start with a Numpy array. I map that array into a torch tensor. I take that torch tensor, map it back into a Numpy array, and then I just compare if all the elements of the recreated Numpy array are same as the elements in the original Numpy array, and it is indeed the case. Also, all this code and stuff is available in a notebook in the GitHub repo, which is linked in the end. Cool. So all good so far. It seems that a lot of functions that I use are already supported. Even if there are cases where the functions are not and then if I do not want to rewrite my entire code, I can just pick the pieces of code which I want to change, and I can just put that part of data into torch tensor and use torch's faster acceleration. So you'll have some existing NumPy logic. Then there comes a part of the code where there's a bottleneck. You take your data into torch tensor, run the computations over the GPU. Once you are done with that heavy computation, you bring back your data into the NumPy logic, and then your application goes on. So you don't even need to rewrite the entire thing. Find the bottlenecks, move data in those cases into a GPU device, do the computation using torch, get your results back into NumPy, and let your execution flow as it was. So no one is asking you to replace your entire application. Find the bottlenecks, just replace them. Right. Now, when we do this dot from NumPy thing, we are basically creating a CPU copy of the tensor, a CPU copy of the data. But I said that the real acceleration, the real benefit comes when you are using a GPU. So how do I tell Torch that, hey, you have a tensor, can you put it on a GPU device and do whatever stuff you have to do on the GPU and get me back the results? So it's very, very easy to move data from a CPU to GPU. By default, whatever data you create would be created on a CPU, and then you can just push it on a GPU. In fact, you can push it on multiple GPUs. No one is saying that you have to use just one GPU. So we have the concept of device. So Torch would allow you to create these devices. When I write torch.device CPU, I get a CPU device. And when I write torch.device CUDA 0, CUDA says that it's a GPU device, and 0 says, so let's say you have got 4 GPUs in your machine. The GPUs would be indexed 0, 1, 2, 3, not 1, 2, 3, 4, because, well, programmers. So you would have CUDA 0 refers to the first GPU, CUDA 1 would refer to the second GPU, and so on. So you have a CPU device, you have a GPU device, create whatever tensor you have, and then just say dot to, and to whichever device you want to send it. In fact, you can have GPU device 1, GPU device 2, GPU device 3, 4, as many GPUs you have. Create those devices and just push your data from one GPU to another, or from one CPU to GPU, and so on, as you like. So again, pushing data from one device to another is very, very, very easy. In fact, PyTorch has, like, at least for the devices which are using NVIDIA kernel, it's kind of more optimized specifically to make sure that the data copy from CPU to GPU is faster. I can't speak for other GPU devices. So again, the point, it's not super expensive, and it's very, very developer friendly. Like, as a developer, there's no cognitive workload. I don't have to write super complex stuff, and it's fast in practice as well. Right. So if I'm using both PyTorch and NumPy at the same time, there are certain things that I have to be careful of, which are more like things that can often go wrong. So first thing is, I start with a NumPy array, I put it into a torch tensor, and then I modify the torch tensor. And if I look at my NumPy array has also changed. This goes back to the point where I said that they are sharing the memory. No one is creating another copy of your data. It's just a view defined on top of your data. So if you manipulate your torch array, your NumPy array is also going to be modified. This is good at times. In fact, this is good probably most of the time, because you're not creating redundant copies. But if you do need to create a redundant copy specifically, then instead of using the from NumPy, use the tensor function, which would look something like this. So you do a torch.tensor. And in this case, it's specifically going to allocate a new piece of memory. And now your NumPy array would remain untouched. The second pitfall is, well, it's really, really easy to move data from CPU to GPU, but there's still some cost involved. And it's not recommended that you move data between CPU to GPU or GPUs every step. So ideally, move data to GPU once, do whatever stuff you want to do there, and then bring the data back. Like, try to minimize the number of hops between a CPU to GPU, because that still has some cost. It's along the lines of saying that try to batch your data together, send all that data to GPU once, do all the GPU stuff you have to do in one go, and then bring the data back instead of keep sending the same data here and there. Right. The other pitfall is, good. So okay, this is a bit cut off. Okay, so I took the torch tensor and I sent it to a GPU device. Now when I modify my torch array, it would not be modifying the NumPy array because the torch array does not exist on CPU. Since I took the torch tensor and I pushed it into the GPU, whatever changes I'm doing there have no effect on the CPU NumPy array which I have. So if you were hoping that since it's from NumPy and the memory is being shared, yes, but only as long as your tensor is residing on the CPU. Once it goes on the GPU, there is no relation between the NumPy information and the tensor information. So this is something that can again go wrong if you are relying on the torch array and the NumPy array to point to the same memory location, because torch array is not existing on the CPU at all now. This is not exactly a pitfall. This is just some common mistake that we tend to do. If you have a device if you have a tensor already on GPU and you're directly trying to bring it into NumPy, it's going to fail. And you would first have to bring your data on the CPU device. You could say that it's a bit of annoyance and PyTorch would kind of handle it internally, but there are good reasons for still sticking with this kind of, there are still good reasons for sticking with this and throwing an error explicitly. So if you have data on the GPU device, you first bring it to the CPU device and then you bring it back into NumPy. Yes, this was the third pitfall. What if I do not have fancy GPUs, but I still want to use PyTorch? Would PyTorch be slow for me as compared to NumPy? I've been using PyTorch for 6 months. I'm not going to give any numbers in the sense of benchmarks, but I have not seen any performance differences. Initially, my workflow used to be like this: do all the pre-processing in NumPy, push the data into PyTorch once you are ready to kind of do the machine learning stuff, and then bring it back. Now my workflow is do everything in PyTorch. And I have not really seen any performance issues or anything. But if in your particular case you find that your operations which you're trying to do are super slow or something, you go to the repository and file an issue. The developer team is very, very responsive, and they try to make sure that there is no speed differences. What about things like QPy and other libraries which allow you to execute NumPy operations on GPU? Well, QPy is basically a drop-in replacement for NumPy. All your NumPy operations remain exactly the same, and now they are running on GPU, which is a very, very useful thing. So why should someone not use that and use PyTorch? Well, PyTorch has got these two perspectives. First perspective is allowing you to use a better hardware, and the second perspective, which we have not talked about so far, which we are going to talk about now, is that it gives you better primitives, better operations. This was the second part of appeal as to why use NumPy arrays and not list, because NumPy array has got a lot of inbuilt functions already. So if your use case is simple, that you just want to have you just have this matrix operation, you want to fasten it up, and you don't really need anything beyond NumPy, then yes, QPy is probably the right thing for you, because you'll get an exact API match and everything. But if you want something, if you want to have better primitives or better data structures, something which is built on top of these tensors, and something that you can use for doing things like even basic stuff like linear regression and so on, then probably PyTorch is a better place because it gives you better primitives for those things. So the part of this appeal is PyTorch is more than this tensor manipulation library. It's an entire deep learning platform, and it allows you to handle your simple machine learning use cases as well as your complex machine learning use cases. If you are a data scientist or a data engineer who is already using NumPy, who wants to get started into these more complex models and is not sure what's the right place, and want to have this NumPy kind of comfortable API or library, then PyTorch is probably the best place for you. You can start with the torch.tensor thing. You'll find the API very, very comforting, very similar, and then you can build from that. And for that, I have got this one example which I have copied from this University of Toronto website, where this person has written linear regression in NumPy. I just took the gradient function, and looking at the code, can you tell me whether this is NumPy or PyTorch? It's both. The part of the appeal is people who are using NumPy and who are doing simpler use cases like linear regression, logistic regression, and so on, they would be writing these things in NumPy. They do not have use case where they want to do heavy operations on deep learning and stuff. But the point is, if you're writing a NumPy operation already, you could write that exact same thing in PyTorch, and that kind of eases the cognitive workload. Now, when you want to start using PyTorch, you won't be looking at it as a new magical framework. You already use tensors, you already use NumPy arrays, so you already use tensors. And once you are in this kind of habit of using these tensors and so on, you would not be writing gradient functions at all. Like, again, I'm not going to talk at all about how PyTorch would do it, but really, this code would be replaced by a one-liner. The main problem that I see when people try to migrate from data science to more advanced machine learning use cases is that this transition is missing. They're happy to write linear regression and they're happy to write the gradient functions, but when someone asks them to use more complicated tools, then it starts to become a problem. NumPy to PyTorch it's very easy if you're just talking about the tensor stuff, and once you're comfortable with using PyTorch, you can start building on top of the APIs and libraries and ecosystem which PyTorch supports. So think of this as an easy way to migrate from simpler data science machine learning use cases to more complex machine learning use cases while sticking with an API that you are comfortable with. And once you can, instead of writing this gradient thing, you could use all sort of libraries which are supported, which are supported by PyTorch for specific use cases. I'm again not going to talk much about that. I just have one tweet by Andre, who is a pretty famous researcher. He tweeted this about using PyTorch. Before PyTorch, people still have a lot of options for using deep learning frameworks, but this is his tweet after using PyTorch for some time. So I will let the tweet speak for itself. Right, so what other benefits? Well, tensors can be easily converted into arrays and the other way around. So even if you do not really have those deep learning kind of use cases, you could use PyTorch to play with scikit-learn, SciPy, and so on. In some cases, there would be specific wrappers as well. For example, we have something called as Scotch, which is scikit-learn plus PyTorch. And the cool part is, if you are using PyTorch and there are certain things which are missing, you could always go back into NumPy, do those operations in NumPy, and bring it back into the PyTorch ecosystem. This is something that I did. It was some previous old version of PyTorch which did not support a specific operation which I needed. My entire computation, my entire processing would be in PyTorch. At that one step, I will go into NumPy, use that function instead of implementing it myself in in PyTorch because I'm lazy, and then I'll bring back data into the tensor thing. So no one is saying that you can only use NumPy to PyTorch. You can do the other way around as well. But that doesn't mean that PyTorch is the perfect thing. Of course, there are things missing in PyTorch. For example, there is no feature parity, access versus dim. It's a minor thing, but it's still annoying at times. And if you have use cases which rely heavily on sparse tensor, then probably PyTorch is not the right thing for you. As of now, support for sparse tensors is quite limited, which would definitely be improved in future. Where do I go from here? Go to pytorch.org, download whichever version, whichever OS and packaging manager and stuff you use. If you are more of a cloud person, then they have ready-to-use cloud disk as well. PyTorch's first major production release is going to be in December 2018, which is less than 1 month now. The kind of broad consensus is that we can expect the API to get closer and the PyTorch API to get closer and closer to NumPy's API wherever it's appropriate. And there are other benefits which PyTorch has other than the deep learning story, which I did not talk about, which are things like distributed package for all sort of computations, which I would skip for now. The point being, PyTorch gives you a lot more flexibilities over NumPy. And of course, there are places where they are not exactly the same, but you can always do a dot to NumPy or from_NumPy. Check out the repository. The code is very user-friendly. It's very easy to read. And they have a very vibrant community where the code developers often come and reply to your issues. And I should thank Adam. Adam is a co-developer of the framework, and he was super supportive in making these slides. All the stuff has been taken from numpy.org and pytorch.org, and that is all from my side. Thank you.